안녕하세요. 4차 산업혁명 기획 7주 2차 시강의를 시작하겠습니다. 오늘의 주제는 챕터 9 첨단 소재입니다. 확대되어가는 첨단 소재의 응용 분야입니다. IBM의 메이어스는 이렇게 말했습니다. 신소재가 생활의 일부분이라는 말은 현실을 매우 과소평가한 표현입니다. 역사를 석기시대, 청동기시대, 철기시대로 나누는 방식만 봐도 신소재 개발은 역사적 관점에서 혁명적인 사건입니다. 도구의 진화는 각 시대마다 혁명적인 삶의 변화를 가져왔지만 최근 들어 발전 속도는 더 가속화되고 있습니다. 이런 관점에서 반도체라는 신소재는 현대 사회를 혁명적으로 변화시켰습니다. 컴퓨팅과 통신 기술의 보편화는 지난 40년 동안 반도체 기술이 100만 배 이상 발전한 결과입니다. 기초 소재 과학의 엄청난 발전에 힘입어 지난 40여 년 동안 사람을 달로 보내는 것에서 시작해 스마트폰으로 640억 바이트의 데이터에 매일같이 접속하는 시대에 이르렀습니다. 문제는 그러한 추세가 영원히 지속되지는 않을 것이며 심각한 결과가 초래될 수 있습니다. 반도체 소재의 꾸준한 발전 덕분에 트랜지스터 크기를 원자 수준으로 줄일 수 있었습니다. 이 단계에서는 양자역학적 행동이 나타나 소재의 차세대 적용을 위한 노력이 무용지물이 됩니다. 따라서 대안을 찾기 위한 첨단 소재 연구 개발에 관련 기업들이 박차를 가하고 있는 것입니다. 대안을 찾기 위한 IBM의 연구 방향은 퀀텀 클라우드 컴퓨팅입니다. 관련 동영상을 보시겠습니다.
There's tremendous mind share out there that we can bring into IBM from using our quantum experience. It is kind of like peering into the unknown. Our quantum experience is currently open to the entire world. Anybody can sign on, register, and start using it. We want to see the best ideas out there. We want to be able to find new algorithms, and we'd love to work together with different individuals, different organizations to help explore that frontier. One of the real surprises to me has been the amount of usage that we've seen in the past 6 months. We're seeing researchers who are actually writing papers and doing new algorithms and testing new theories using it. Educational institutions, professors using it as part of their coursework. So we're really starting to see this ecosystem building, and we're really hoping to continue that as we get towards these larger systems where we really want to find the areas of application.
In terms of applications, I think one type of really big challenge that many of us who are working on this really want to be able to solve is to see the simulation of chemistry, a simulation of nature. But what we care about is unlocking those secrets. If you're gonna try to understand nature, which is naturally quantum mechanical, there's no reason to use bits, zeros and ones to do it, but to actually use other objects that follow those same natural laws, quantum bits, to try and simulate them and try and understand them. The implications for this are huge with regards to designing new drugs and designing new materials, understanding catalytic interactions and different types of molecular interactions that are just too difficult and too complex to brute force calculate today. With quantum computers, we really have that potential to look for solutions and calculate things which we never thought about before.
다음은 인텔의 연구 사례를 보겠습니다. 물리적 한계의 해결책은 없지만 성능 개선을 위해서 지속적으로 노력하고 있습니다.
This is Lakefield, the first CPU architecture to take advantage of Intel's latest processor design and packaging innovations. These recently announced breakthroughs allow us to integrate different CPU core architectures onto a single product to create what we call a hybrid CPU. In this example, the processor has 5 cores, combining one 10nm high-performance Sunny Cove core with 4 10nm based smaller cores. The result is a product that is optimized for power efficiency, immersive graphics, I/O, and memory, all in this tiny SoC, which is approximately 12 millimeters squared. We then pair this hybrid CPU architecture approach with an innovative 3D packaging technique we call Foveros that allows us to actually stack various pieces of IP together in 3 dimensions rather than 2. The result is a tiny SoC that is now packed with all the no-compromise PC technology that people have come to expect from Intel, driving longer battery life, world-class performance, and blazing fast connectivity. All of which means we can now do much smaller chips and much smaller boards while maintaining great performance in highly power-efficient designs, which is why we expect this technology to unleash a wave of platform innovation industry-wide, creating entirely new classes of highly mobile devices and helping to advance PC innovation by bringing new experiences to life.
다음은 인텔이 자랑하는 반도체 제작을 위한 마스크 공정에 대해서 알아보겠습니다.
This, an Intel mask. Cool thing number 1, the intricate process. Wafer manufacturing cannot start without masks. A mask is a template that we use to print circuitry onto a silicon wafer. To create a mask, IMO engineers use computerized drawings from Intel chip designers that are the blueprints for our chips and their billions of transistors. Those drawings are fed into the machine that converts the data into an electron beam. Those electron beams scan the surface of the mask and print the circuitry pattern onto it. Every mask needs to be perfect, 0 defects. It takes about 5 days to process a completed mask. IMO techs then send them to factories where manufacturing techs use stepper and scan machines that shine light through the mask, then through a lens to reduce the image, and then onto the surface of the wafer, creating hundreds of individual die. To print the many layers of an Intel 14nm die requires more than 50 masks. To support current and prior generation technologies in our global factories this year, IMO will make thousands of masks. Cool thing number 2, the data. Take a look at this famous 1978 photo of Andy Grove, Robert Noyce, and Gordon Moore. On the table in front of them is a mask made of mylar. It's about as big as 2 Monopoly boards. The mask is a design for our 8080 CPU. Each circuit line you see on it was hand-drawn. Today's masks are 6 by 6 inch pieces of quartz, a 1/4 inch thick, and include blueprints for billions of transistors at the nanometer scale. Each line on the mask is smaller than the wavelength of light used to print them. One 14nm mask contains the equivalent of about 5 petabits of data. That's 10 times the amount of data used in a 2-hour digital IMAX movie. And finally, cool thing number 3, our competitive advantage. Intel is one of only a few semiconductor manufacturers in the world with its own in-house mask operation. Our mask operations, located in Santa Clara and Hillsboro, Oregon, are considered the best in the industry. Our factories in the US, Ireland, and Israel depend on IMO to pump out masks every day. They begin each of the hundreds of repeated layer steps a wafer undergoes in the fab. Behind every mask is a face, and behind that, a story.
이 엄청난 도전 과제 앞에서 정보기술 발전의 지향점, 그리고 이를 위한 기술 연구에는 대전환이 필요합니다. 첨단 소재를 개발하려는 시도 중에서 사회적으로 영향력이 없는 것은 없습니다. 20년 내로 세계 인구가 수십억 명이 증가할 것이라고 예상되는 만큼 식수 공급 문제를 생각해 봐야 합니다. 급수장의 부족에 따라 담수와 같은 에너지 집약적 물 공급원은 공급량을 보충하는 중요한 수단이 될 것입니다. 만약 이 옵션을 적절한 규모로 키우려면 이 프로세스의 기초기술이 되는 역삼투를 통한 수질 정화에는 그 어느 때보다 효율적인 막재료가 필요합니다. 하지만 막재료가 유의미한 수준으로 발전한다고 해도 방대한 새로운 에너지원이 요구됩니다. 이 문제를 해결하기 위해서는 첨단 소재의 도움이 다시 한번 필요해집니다. 미래의 물 부족은 상당히 심각한 문제입니다. 바닷물을 담수화하는 것에 대해서 알아보겠습니다.
71% of our planet's surface is covered in water. 332.5 million cubic miles of it. 366 billion gallons. That's over 48 billion gallons of water for every person on Earth. But today, 1 out of 3 people don't have access to safe drinking water.
Some projections will show by 2050, more than half our population will be living in water-stressed areas. That's over 4 billion people.
These aren't just issues in developing countries, something you hear about elsewhere. These are things that are happening in our communities all the time.
Worried and angry about lead contamination.
The military in remote parts of Puerto Rico.
And that's the result of many things, but one of them is that 96.5% of that water is found in our oceans. It's saturated with salt and undrinkable. And most of the Earth's fresh water is locked away in glaciers or deep underground. Less than 1% of it is available to us.
When you dig a little bit and look under the surface, even here in the United States, we have large numbers of people that don't have access to safe, clean drinking water.
So why can't we just take all that seawater, filter out the salt, and have a nearly unlimited supply of clean, drinkable water?
Desalination, broadly, is the process of removing salts from water. It's been practiced for years. In fact, it's a natural process. It occurs when the sun heats the ocean and fresh water evaporates off and it falls again as rainfall.
If you mix salt into water, it dissolves. And if you could watch microscopically while you did that, you'd see that the water is actually breaking apart the salt into charged particles that chemically interact with the water. So salt water is a chemically new solution. It's not just water with some salt grains floating around in it. And that's why desalination is a fundamentally tricky process.
The two main types of desalination are thermal desalination and reverse osmosis. Thermal desalination is the oldest form of desalination.
It's essentially boiling water and then capturing the steam and turning that into fresh water. But in the 60s, we were able to develop reverse osmosis processes at UCLA, and these have now started to dominate the market. So one of the big chief differences between the two is reverse osmosis doesn't use heat, doesn't boil anything. You're really just pressurizing the water to a tremendous amount and you're forcing it through a membrane where it doesn't want to go. It wants to stay with the salt, but with this high pressure, it is forced to separate from the salt. Broadly speaking, what you want to look at for desalination is where's my fresh water coming from and do I have enough of it? And if I don't have enough of it, do I need to augment supply? Desalination then starts to become a very attractive or interesting option.
Which is why the vast majority of desalination efforts right now are happening in places like the Middle East and North Africa, rich with fossil fuels, but also experiencing extreme water scarcity.
Just two countries, Saudi Arabia and UAE, they produce 1/4 of the desalination water that is produced currently on this planet.
Concerns about desalination fall broadly into 3 categories: the amount of energy required, how much it costs, and its environmental impacts.
There are some that really see it as a key solution. There are others that push back and argue that it's very energy intensive, it's very expensive, it has impacts on the marine environment, and that we should pursue alternatives first.
It requires a tremendous amount of energy to basically break up that bond between the water and the salt. Ocean water desal can be 25 times as energy intensive as other freshwater approaches.
Historically, the impediment for seawater desalination being more abundant or popular in North America has been cost. It has been cost prohibitive historically.
결국 물 부족의 문제는 코스트입니다. 첨단 소재 개발과 에너지 문제에 대한 해결이 필요합니다. 지구온난화를 악화시키지 않으면서 전력 생산 능력을 확보하려면 에너지 생산 관련 소재의 획기적인 발전이 선행되어야 합니다. 재생에너지 기술은 관련 소재 발전의 덕을 누릴 수 있습니다. 하지만 이보다 더 중요한 것은 배터리 기술을 크게 향상시키는 신소재 개발을 통해 신재생 에너지를 보다 효율적으로 저장하고 발산하는 능력일 것입니다. 테슬라도 전기자동차의 배터리 발전을 위해서 많은 노력을 하고 있습니다. 동영상을 보시겠습니다.
When Tesla introduced its first model back in 2006, it was hard to imagine that in just 14 years, the automotive world would be on the verge of a new revolution. Governments of different countries introduced different support measures at the legislative level by subsidizing the sale of electric cars both directly and through various bonuses. However, this whole rainbow world is currently facing a big problem, namely the limited capacity and high cost of traditional lithium-ion batteries. But it's also obvious that lithium-ion battery technologies have advanced significantly over the past 5 years. Modern batteries are known by advanced solutions that provide both a long-range and relatively faster and safer charge. Such a breakthrough was made possible since leading chemical and technological companies, for example LG Chem, Panasonic, etc., set about manufacturing batteries for electric cars. But that's why, regardless of cars' brands, they are all dependent on third-party suppliers. Tesla's partnership with those companies has led to an industry-leading battery cost, but over the past few months, the automaker has been rumored to be working on making its own battery cells in the Fremont factory. At the same time, the company has already spent its quota on government subsidies, so it needs breakthrough solutions that will help strengthen leadership over its competitors, such as Volkswagen and BMW, etc. And the first and probably the most logical step on this way is to create a cheaper and more capacious battery pack. The still secret project is called Roadrunner, that aims at achieving mass production of a new battery cell that comes with more energy density and a lower price. Although there is no clear statement from Tesla on starting the battery production, there is enough indirect evidence of their work. The company has bought cell production lines at its Nevada factory owned by Panasonic and acquired Hybar Systems, a well-known company providing state-of-the-art equipment for battery cells manufacturing. The revolutionary leap in terms of development of new battery design is likely to occur through the acquisition of Maxwell Technologies from San Diego. Maxwell is specialized in developing ultra-capacitor energy storage technologies made with dry electrodes, and is actively exploring the solid-state technology. So, what are the main advantages of dry electrode batteries in comparison to the current cells? One of the key advantages is the formation of a durable and tough electrode, which can significantly increase the battery's life. It's not accidental that Elon Musk announced the new battery pack designed explicitly for 1 million miles of operation. This achievement will obviously provide better resale value for the vehicles. The second benefit is the higher energy density that ensures more range for an EV equipped with the dry electrode. According to the manufacturer, the energy consumption of more than 300 watt-hours per kilogram has already been achieved on the battery prototypes using these technologies. The challenge for the future is a breakthrough to the energy density level of more than 500 watt-hours per kilogram. And finally, dry electrode batteries are easier, faster, and cheaper to manufacture, giving low-cost pilot manufacturing capabilities, thanks to which the batteries will cost $100 per kilowatt-hours already in 2020, which will enable the price of Tesla's batteries to drop by about 20%. The environmental benefits are that these new technologies feature environmentally friendly materials without poisoning solvents and dangerous cobalt. So, we might shortly see Teslas on the road that will be equipped with cheaper cells with higher energy density that would enable the vehicles to achieve longer range with less batteries. This will help Tesla to jump once more over its closest European rivals by offering efficient EVs with much more affordable price, which could be comparable with most popular ICE vehicles. We could expect more information during Tesla's Battery Investor Day event later in April, when Elon Musk will probably announce the production of the battery cells. The next achievements in the processes of battery evolution will be the solid-state batteries, about which we will speak in one of our upcoming videos.
우리 사회는 더 많은 천연 자원을 계속해서 필요로 합니다. 이 당면 과제를 조금이나마 해결하기 위해서는 많은 기술 혁신과 사회 혁신이 요구됩니다. 신소재 개발이야말로 우리의 가장 긴급한 문제를 해결할 수 있는 방법 중 하나입니다. 어펜딕스입니다. 지금까지 시청하신 것으로 이번 차수 수업이 인정됩니다. 관련 동영상을 보시겠습니다.
The technology we're bringing to market would be able to boost energy density by about 20%, and then over the next couple of years we'll push it to about 40% improvement. The existing chemistry improves maybe 2% every couple of years, so we're really bringing a new battery chemistry to market for the first time in about 30 years. As I spent more time looking at batteries, it really turns out to be one of the hardest problems in the world.
Since its introduction in the 1990s, the rechargeable lithium battery has been the standard for everyday tech devices and electric vehicle power. As the world races toward an electric future, it needs something better to keep pace. Battery startups trying to build better batteries, ones with lower costs and better performance, believe big improvements are coming.
The lithium-ion chemistry has really reached its theoretical limits. Sila is a materials company that was founded with the mission of moving us to a new generation of battery chemistry, and that new generation of battery chemistry will enable further advances in energy density that'll allow electric vehicles to go further, be cheaper, as well as make for better consumer devices.
Sila is one of several startups that received major funding to continue working on their technology. Now, after about 10 years of research, they'll soon be ready for the commercial spotlight.
Things like wearable fitness trackers, smartwatches, wireless earbuds, cell phones, but it really is going to take us quite a lot of scaling up before we're in electric vehicles. And the hope is really to start in electric vehicles where we can deliver the highest performance, and then as we're able to produce the material at a larger and larger scale, bring down its cost and further bring down the cost of the battery, we would want to be in every passenger electric vehicle produced.
To do that, Sila has replaced the graphite in today's batteries with silicone to create silicone anode batteries. They say this change can deliver a better performance from a cheaper product.
The current lithium-ion battery uses what is called an intercalation chemistry. It has a graphite anode material and a metal oxide cathode material. And those materials are then assembled and wound into a cell that would either go into your electric vehicle or your cell phone. What we do differently is we replace the graphite anode that's in the battery today with a proprietary material that we've synthesized. And that material is able to store energy more densely than graphite, and so it allows us to pack more energy into the same cell. The simplest way to think about that is if we can store twice as much energy, let's say, in the battery that you use in your electric vehicle, then you need half as many batteries to go the same distance. And if you need half as many batteries, it'll cost you about half as much.
This could mean longer-lasting gadgets, cheaper electric vehicles, and ultimately, a cleaner power grid.
What grid operators and utilities are going to want is predictable solar and predictable wind. And the way you get to predictable solar and predictable wind is to have energy storage coupled with it so that whenever the wind is blowing, you're charging the battery, and whenever the utility needs the power, you're discharging it. So we think that this chemistry is a huge accelerator for being able to deploy renewables from a few percentage points on the grid to replacing most fossil fuels around the world.
The long development timeline for these startups is a sign of how difficult pushing battery technology can be.
We're in our 8th year of operation as a business. We've raised about $125 million to date just to get to a place where we've solved the chemistry problem. It's that hard. It's taken almost a decade just to make the technology work. And so now the challenge shifts for us to really scaling it up. And it requires everybody to work together to get to the right answer. We have a deep belief that new battery chemistries become the standard after some years. We've seen that before, and so as we start to launch this chemistry, so long as we can get our production volumes up, then we expect that this chemistry or these kinds of chemistries will become the de facto standard for the next generation or so.